So this first example of kind of a pulley problem, which we will go back to. This first example, we've got a block of mass M1 sitting on a table or sitting on a horizontal frictionless surface. And it's pulled by a light string that passes over a frictionless massless pulley. So you can imagine you got a pulley like this. And the other end of the string is connected to a block of mass 2, which hangs off the edge of the table. Find the acceleration of the blocks and the tension in the string in terms of M1, M2, and G. So what we want to do whenever we've got a dynamics problem like this, we want to first draw our free body diagrams. So for M1, we know that it's going to be pulled to the right with a tension force, whatever the tension in the string is. We know it's going to be pulled to the left with actually nothing because it said there was no friction. So it's not going to be pulled to the left at all, excuse me on that. It will have a normal force pushing it up from the table. It will also have a downward gravitational force because it's pulled downward by, gravity. Likewise for M2, what happens here? Well, we always have gravity, so we'll have Fg, and let's distinguish these by calling these Fg1 and Fg2. And it will have some tension force pulling it up because the rope's attached above it, and the rope's going to slow it down, or the string is going to slow it down, whatnot. Now we're going to write Newton's second law for both of these. So for M1, notice that the up and down forces will cancel. We don't expect any motion up and down. We just expect horizontal motion. So we're going to have net force on object 1 equals MA, M1A, A1. And the net force on object 2 will equal M2, A2. Now if we actually plug some things in and work on it, we can see that Ft should equal M1, A1, and Fg minus Ft should equal M2, A2. And this is because I'm going to assign positive to the right, negative to the left, positive down, negative up, just because I expect it to go to the right and down, so I'm just going to put my positives in those directions. Now, we know that Ft is the same for both of these because it's the tension force in the string, and we know tension force is constant throughout. We also know that Fg2 here should be mg. And what you may not have realized, but we can justify now, these A's have to be the same. A1 has to equal A2. And the reason for this, if M2 accelerated faster, or had greater acceleration, that would mean it would get ahead of M1. It would move more than M1 would, right? Because if it has greater acceleration, it travels farther in the same amount of time. What would have to happen to the string? It would have to stretch or break, and we're assuming neither of those happen. Conversely, if A1 was bigger than A2, that would mean that the blocks get closer together and the string would bunch up. Well, if the string bunches up, then the tension force goes away because it's not pulling anymore, it's bunched up. So that means A1 has to equal A2, so we'll just call it A for convenience here. And now we'll have the system of equations that F2 equals M1A times and the second one would be M2G minus Ft equals M2A2. Now we can put this Ft down here. We can substitute in the M1A down here. And we get M2G minus M1A equals M2A. Sorry, that should just be A. Doing some algebraic rearrangement, we will get M2G divided by M1 plus M2 equals A. So that's the acceleration of the system. That's the magnitude of the acceleration. And now we just need to find the force. Well, we already know the tension force is m1 times A, so it's just m1 m2g over m1 plus m2. Yeah, because it's m1 times A is m2g over m1 plus m2, so that will equal our tension force. So to summarize, what we started with was a free body diagram for all the objects involved. Then we wrote a system of equations of the F equals ma, or the net force equals mass times acceleration for both. And then we just solved that system of equations for the two unknowns, A and Ft. The next one will be a slightly more involved problem that I'll show you kind of a shortcut or a trick that we can sometimes use.